So I've been using iOS amp sims for years, and the first one that came out was Amplitude, and I remember I was so excited by the advertisements that it said, you know, this is, well, even the name, it sounds like this is going to be a tube amp, and it's going to run on your computer, and you won't have to buy all that hardware. And so I got the first connector I got was the iRig, and I was plugging my guitar in, and I tried all of the amp sims, and I just didn't really dig the sound that was coming out. You know, the Marshall, the one that looks like a Marshall, it kind of has a Marshall-y tone, but then it has this kind of this weird noise that's always going on in the background that I don't remember hearing from any of my tube amps. I don't actually own any tube amps anymore, but I used to. And so for years I've been kind of waiting to see, like, when is iOS going to get an amp sim that I can plug my guitar into and not have another amp and feel like this is really a reasonable substitute. And then a few months ago we did a video about our compressor app where we were looking at the question of aliasing, and after doing that video, I got the idea that, not really an idea of how to solve the problem, but just an idea that I should set a goal for myself. I'm not going to build an amp. I'm not going to even simulate a tube or a transistor. I just want to know, is there any way that we can do overdrive distortion or saturation on a computer that would allow me to have 100 decibels of input gain and still not alias at the output? So that's the question that I asked myself a few months ago, and I've been working on this almost every day for the last few months. And recently I got a result that's really interesting and it looks really good. And basically it says that with a combination of techniques, yes, we can do high gain guitar amp type distortion, and we can do it on a computer without the aliasing noise. So we're a long way off from building a complete guitar rig, but what we do have is, I think, one of the key components that I've been waiting for years, and that is we can do the high gain distortion now, and we can do it on iOS efficiently without aliasing. So in the remainder of this video, after this intro portion, I'm going to talk to you a little bit about what aliasing is and where it comes from in the context of amplifier simulators. And then I'll show you some demonstrations of the new thing we've got going that is able to actually do 100 decibels of input gain, which is a really high gain input, and do it with I won't say a clean output, it's a distorted output, but it's an analog type distorted output. So I'm really excited to share this with you, and please enjoy the rest of the video. This graph that you're looking at is something that we used for a video several months ago when we released our compressor plugin. So this is a graph of a stereo output of a sine sweep, and you see this yellow whitish line represents the sine sweep itself. And then anywhere other than the sine sweep we don't see anything because there's nothing else there. There's just black darkness. And we compared all the compressors that I could put my hands on at that time from the iOS platform. And we were doing that because we had just made a compressor, and originally we wanted to know for ourselves where our own compressor sits in terms of sound quality. And then also, of course, we wanted to share that with our customers so that they know what they were buying. So this is the output from our own compressor, and it turned out to be the cleanest of all the compressors, so clean in fact that you don't really see any difference between the original signal and the compressed signal. And as we looked at other compressors, we saw differences between the original sine sweep and the compressed output. So here's an example of that. This compressor is creating some harmonics, and you see them above the original sine sweep line, and these are going to add some nice tone, and then there are these lines on the side which represent aliasing, which is a digital error creates a number of different sound artifacts, but essentially they're going to sound like noise, either like a type of noise or like an additional frequency that doesn't fit with the music. So what we're seeing in this case is going to come out sounding like another frequency, because you can see the noise is very localized in a certain frequency range, but it's not a frequency that corresponds to the frequency of the input. And here's another example of a compressor with a different type of distortion characteristic and a different type of aliasing. This type of aliasing would be more likely to have that kind of hiss noise to it. This one is a very extreme example with a lot of aliasing noise. This one has a lot of aliasing noise at high frequencies, but it's very clean at low frequencies. This would work really well if they oversampled it. I'm noticing the frequency that it starts having aliasing when the input hits about 4 kilohertz. So if they would just oversample by a factor of 8, then this aliasing would have been eliminated from this compressor. We're not going to talk about compressors today. The question that came to my mind after I looked at these is I was thinking, would it be possible for us to design a compressor that has these analog style distortion harmonics but not having the aliasing? And I haven't answered that question definitively yet, in the sense that we haven't actually built such a compressor, but I thought a good first step would be to work on building a saturation effect, because that would give us an understanding of what causes the saturation to occur. I mean, theoretically we know, but we wanted to really get in deep in understanding where it's coming from and how it happens. And then also it would give us an opportunity to find out how we might be able to stop it or prevent it or reduce it. So that's what I want to talk about today, is some of the interesting things we learned as we've been studying how to reduce reduce aliasing and a saturation effect. So I have this file which just is to give you a few basic ideas about what saturation is and why it aliases and what that looks like. So this graph on the left represents an input-output function. So the input is on the x-axis and the output is on the y-axis. And this is a function that I'm calling here the identity function. And called the identity because it returns exactly what you put into it. In other words, this is what the graph looks like when you're not doing anything. You're just taking sound in and sending it to the output without any changes. So one of the simplest ways that we can apply saturation is to apply something called wave shaping to the output, which to the signal, which means that rather than just taking the signal from the input and copying it straight to the output, we'll change the volume of the signal, of the output signal, depending on the volume of the input signal. And that's what we have on the right. I've solved some polynomial equations and come up with a very simple wave shaping formula here. This is, I mean, I said I've solved it, but other people have solved this before. This is a very well-known formula for third-order polynomial wave shaping. So what this does is it boosts, if you compare, it's a little bit hard to compare the left and right side by side. Actually, I could throw these on top of each other, which would make things easier for you. Let's do that quickly. Change this to show and delete these things. Let's see if that gives you, yeah, there we go. So now we have the two on top of each other. So the straight line is what you get if you're not wave shaping, and then the curved line is wave shaping. So what happens is we're boosting, the wave shaping is boosting the input a little bit when it's between 0 and 1, and then after it gets to input value of 1, it cuts it off flat at the top. So that when we apply this kind of wave shaping function to sound that's within the clipping range, so it's between -1 and 1, which is the standard range for digital audio signals, it's going to boost the volume a little bit, and then it will also create some harmonic distortion that we'll see in just a minute. So this example is showing what actually it looks like when you run a sine wave. through this wave shaping function. So here's a sine wave, just a standard ordinary sine wave. I haven't done anything to it. And on the right, this is what it looks like. I'm going to go to full screen so you can see this better. On the right, this is what it looks like when you wave shape it. So you can see it's a little bit louder. These curves go up faster, and they're kind of flattened off on the top of the wave. Now another function that is useful for wave shaping is the hyperbolic tangent function. TANH is often the abbreviation of that, and that has quite a different behavior from this polynomial function. So this is the original polynomial function on the left, and the hyperbolic tangent reduces the volume quite a bit rather than boosting it, but it has a much softer clipping at the top. Now this difference is important when we're at low volume, especially if the input was kept within the clipping range, and well, if the input was in the range from -1 to 1, these differences are significant. But what we find is that when you drive these things really hard, it ends up not mattering a whole lot. Like when you're really starting to hit it with a lot of input gain, it doesn't really matter a whole lot as long as you have a soft curve. They all end up doing basically the same thing when you boost the gain up really high. So I'm going to do that. We're looking at the, what function is this? Hyperbolic tangent function. And I'll click this so you can see what my gain is. So here's 0 dB of gain. So this is a little bit of gain cut, 6 dB of cut. As I hit 0 dB of gain, you start seeing something similar to what we saw up above. And as I go past 0 dB, you're going to see it starts to flatten off at the top in a similar way to the polynomial function we saw before. And as I drive this harder, here's 20 decibels of gain. Here's 30 decibels. Here we're going up to 40 decibels. This graph will neaten itself up when I take my mouse off, because when I'm moving this, it draws with a more efficient graph function. So at 40 dB, what we see is that it looks basically like a square wave. We can see a little bit of rounding of these corners. If I would go up to 100 dB, then it really just looks like a square wave. Even though, and I think this might surprise some people, because you might think, well, you have this soft clipping function, how are you getting a square wave out of it? Well, when you drive it with this much gain, you're so far above this limit where it's where the wave has flattened off, that this softness down at the bottom end just doesn't mean anything anymore. And I think this might give you an idea of why that's so. So if you have 0 dB of gain boost, that's equivalent to multiplying your input signal by 1. If you have 20 decibels, that means you've taken the input signal and you've boosted it to 10 times, if we're talking about electronic signals, 10 times the voltage of the original signal. 40 dB is 100 times the voltage. And if we go up to 100 decibels of gain boost, that means we're multiplying our signal by 100,000. So that's a mind-boggling, huge boost in gain. And it's such a huge gain boost that it just, no matter what wave shaping function you use, as long as you're limiting the volume somewhere, you're going to hit that limit, and you're going to hit it hard, and you're going to get a square wave out of your wave shaping function. So I'm particularly interested in this case with 100 decibels of boost, because this is so extreme, and yet there's some practicality to it, because if we look at high gain guitar amplifiers, they are in that range. I'm not sure exactly what the number is, but they do need that amount of gain in order to get that really high gain overdrive sound. They have to push the gain at that level. So once again, I'm saying that 100 dB of gain boost is multiplying your input signal by a factor of 100,000 in terms of the voltage level. And that might sound a little bit confusing or hard to believe if you think about a guitar amp boosting at that level, because you don't feel like they're that much louder. And the reason is that this 100 dB gain boost comes together with overdrive and saturation. So although you're driving the gain to this insanely high level, then you're limiting it with the overdrive characteristic, the distortion characteristics of the tubes, so that it doesn't really, in a sense, it doesn't quite get up to that insane level of gain that you're talking about. I'm not sure if I'm expressing that very well. If you look at this, you can kind of see. So here's 40 decibels of gain, which is only 100 times amplification. And when I go from 40 up to 80, watch the difference in the graph. There's almost no difference. There's just a hardening of these corners. But really, as a whole, if you look at that graph, you don't see it getting 10,000 times larger. In this case, it's 100 times larger, from 40 decibels to 80 decibels. It doesn't look like it got 100 times louder. What it would get is it just get more gritty, more high frequency scratching and screeching sound. And also there would be a change in the way it responds to very soft volume levels, so you'd get more noise coming through in the signal. So the goal that I set when we started working on this saturator is I said, let's just try and see if it's possible. Let's see if we can make a saturator that can do take 100 decibels of gain boost at the input without saturating the output. Sorry, not without saturating. Without aliasing on the output. So let's have a look at what the kind of aliasing we get from wave shaping saturators. So here we have a spectrogram of a plain sine sweep with no wave shaping, and this sine sweep has 0 dB of gain boost, so it's limited within the range from -1 to 1, and it has this basically clean output. This spectrogram is not as nice as the one in Izotope RX, but we'll use this for the moment. And then here's the polynomial wave shaper, which is very nicely behaved as long as the volume doesn't go over that -1, +1 limit. I say nicely in the sense that it creates exactly one distortion harmonic. And it aliases exactly at 1/4 of the sample rate. So if we're at 48 kilohertz, the Nyquist frequency is half of that, is 24 kilohertz, and it will start aliasing at 1/4 of that, which is 12 kilohertz. And we see very prominent aliasing. So this is a lot of aliasing, but it could be totally eliminated by oversampling with a factor of 2. But I want you to note that would only work if we don't boost the gain. We have to keep the gain, input gain, perfectly within the limits. It can't clip at all. This is the hyperbolic tangent, and the hyperbolic tangent looks softer on the graph. It looks like a softer wave shaping function than the polynomial one, but actually it creates more distortion harmonics. We can see 1, 2, 3 harmonics above the fundamental, and there's more aliasing going on. But again, this is what it looks like when you're not boosting the gain beyond the clipping level. Now here we look at what would happen if we boost the gain. So I'm adding a 10 decibel gain boost, and this is the polynomial wave shaper, and this is the hyperbolic tangent. And you can see as soon as you, let's say, break the rule and go outside that digital audio limit of -1, +1, the polynomial wave shaper doesn't do well at all. It creates enormous amount of aliasing, creates a lot of harmonics, which is what we're trying to do with a saturator, but this aliasing would be really bad for your sound. You wouldn't want to do this to any kind of audio that you're running. And the hyperbolic tangent, because it's softer, it turns out that it's much better at handling the case where you're breaking the rules a little bit. You push the gain beyond the normal limits. But as we drive both of these further and further, here's 20 decibels of gain boost, we see that they both just become unreasonable as unreasonable in the sense that we couldn't use these for saturation functions without doing some additional work to eliminate aliasing. You can see this level of aliasing is just not useful anymore. And we're only at 20 decibels of gain, which is, we looked at that, which is only a 10 times boost in the volume. I mean, 10 times could be considered a lot, but it's nothing compared to the kind of high gain that we're shooting for. So here's 20 decibels. Do I have more? I've got 40 decibels. At 40 decibels, aliasing is everywhere, and we're not, at this point, we're having that kind of aliasing, we could call it tone aliasing, where a one frequency aliases onto another unrelated frequency that wouldn't sound good. But what we have at 40 decibels is something that would sound more, I would call it noise aliasing, where the aliasing has gotten so extreme that it's not really possible to talk about what frequency it's at anymore. It's just creating a sound. And I've, I haven't studied in depth how the guitar amp sims on iOS work, but I've bought almost all of them, and I'm always a little bit disappointed. I say almost all of them. There might be some good ones out there that I haven't tried, but I'm always a little disappointed with the distortion sound, that I always hear this kind of going on in the background that I feel like I wouldn't have heard on a real analog amp. And I feel like this is what's going on in that case, is that they've got so much aliasing, especially when the amp is at high gain, that there's just constantly noise coming out, and it's not a tonal noise that's related to what you're playing. It's just this hissing sound that's always there. So that's what we're getting at 40 dB, and here it is at 100 dB. At 100 dB, on this graph, it doesn't look even that much different from the 40 dB. The only thing we see is that there seems to be even more of this noise and even less of the tonal stuff. So the question that we might ask next is, what if we oversample? Then what would happen? So here I'm oversampling the 100 dB input, and I think I'm having problems with a spectrogram in Mathematica, so I'm going to switch over to something that I did in C and look at the isotope spectrogram just now. But you can kind of see what's going on here. I think this is wrong, though. What we're seeing here is that there's still plenty of this noise, chaotic noise type of aliasing, but we're not seeing so much of this harmonic aliasing. Like these purple lines have greatly reduced. But I think Mathematica is playing games with us because here this is an oversampling factor of 8. And here I've gone up to 64, and it actually got worse when I oversampled higher. So let's ignore this. We've got other ways to deal with this. Let's have a look at some real, when I say real processing, I guess I mean real in the sense that these are software that we actually use in our plugins for processing audio. So this software you're looking at now is Xcode. This is the main development environment for iOS and Mac software developers. And I'm testing, am I testing what I think I'm testing? Indeed I am, but let's take the gain down to 0 dB. Okay, so what I've got here is I'm generating a sine sweep. I'm boosting the gain, in this case by 0 dB, which does nothing. I am upsampling by a factor of, let's not upsample. So upsample by a factor of 1 means not upsampling. And then I am applying, here's the wave shaper, I'm using the hyperbolic tangent, and then we'll downsample. So I'm going to run this, and it creates a test file which can be exported to wave by running this little script. There we see the first few samples of it, and if I do this, you will be able to see what it looks like in a proper graph. So this is the hyperbolic tangent wave shaping on a sine sweep that was obeying the input laws. It's not clipping. And you can see up to about here. Here is where the aliasing starts. So here's where the input frequency hits about 3 kilohertz. That's where aliasing starts. So looking at this, I can see that we could totally eliminate all of this aliasing just by oversampling. And I can even calculate how much oversampling it would take to do that. If I move this cursor, it looks like we're at about 2.5 kilohertz when the oversampling starts. And this is a 48 kilohertz sample rate of the audio system. So the original Nyquist frequency is at 24 kilohertz. I need to get the Nyquist frequency down so it cuts, it cuts the wave off right here, which is where the aliasing starts. So I need to get my Nyquist frequency effectively down near 2 point some kilohertz. So it's 24. I need to go down. Let's say I need to go down to 2.4. I need a 10x oversampling factor. This particular oversampler only does powers of 2, so I'm going to use. Let's try a 8x first and just see what that does. Make sure our math is coming out right. Run the script to convert to wave. Close this down and reload. Actually, it looks like 8x took care of it. I don't see any aliasing now. So this is just the basic hyperbolic tangent function. We oversample by a factor of 8. Aliasing is gone. So that looks pretty good for oversampling. It looks like we've taken care of the problem, and it looks like we could go and make a plugin now, and we could saturate this way. But we haven't looked at what happens when you boost the gain. So I'm going to do a 20 decibel gain boost. Remember, that means I'm multiplying the volume by a factor of 10. Let's go again and see what we have now. So we can see the wave is getting a lot flatter on the top. It's starting to look more like a square wave. And let's have a look at the frequency domain situation. So even with our 8x oversampling, applying this gain boost has led to quite a lot of aliasing. Now, we're not seeing the noisy kind of aliasing, which is good. We're just seeing this tonal aliasing. And I say that's good because as long as the aliasing is tonal, it tends to stay in a certain frequency range. You can see it's in this range, which means if I just oversample more, I'll be able to get rid of it. So I can even, like I did before, I could even guess at how much oversampling I need. It looks like aliasing starts at about 7 kilohertz, so I need 7 times, how much is 24? If it were 8 kilohertz, that would be 4. I'd need an additional 4 times oversampling above what I already have. So 8 times 4 is 32, and that should be enough oversampling to put a stop to that aliasing. Let's have a look, and indeed it does. Going up to 32 times oversampling has allowed us to eliminate aliasing even when the gain is clipping by up to 20 dB, which is a factor of 10. So let's skip ahead a little bit. Our goal is we want to have a plugin that does saturation and does not alias, period. So that means even if we've used it in a high gain guitar amp type situation with 100 dB of gain, we would like to see no aliasing. So let's see how we're doing. Here's 100 dB of gain boost. I'll run the script again and have a look at the output. So 32, this is 32 times aliasing, 32 times oversampling. And it looks like 32 times oversampling is enough to get rid of all of that harmonic type of aliasing that we saw. But look at how much noise we've got. So what would happen if you were to use this inside of a simulation of a high gain guitar amp, for example? You would definitely hear the sound, the high gain distortion sound, but you'd have a lot of extra noise. Your noise floor is way up. Let's even have a look at what kind of noise level we get here. I want to see the spectrum of this. So my input is coming in at negative 20 dB, and then I've got the noise floor at like negative 70 dB. So we've got 50 decibels of signal to noise ratio. Often people will say that for high gain guitar amps that the distortion, the the analog style distortion harmonics makes so much noise anyway that it really doesn't matter if you have this kind of aliasing noise. And that may be true. I don't know if this is audible or not, because 32 times oversampling is quite a lot. Most plugins we see tend to do 4 times, but let's just out of curiosity, let's look at how far we would have to oversample this to come out with a signal that doesn't alias. So after 32, the next power of 2 would be 64, then 128, then 256. Let's have a look at 256. So 256 times oversampling means we've increased the sample rate by a factor of 256, means every time we process one sample of audio input, the internals of the plugin will have to run 256 samples in order to do that oversampling rate. And we'll run the script and view the output. So you can see the noise is down considerably now that we're at a factor of 256 oversampling, but it's not gone. There's still a lot of noise. Noise is now down to negative 90 dB when the signal is at 20. 90 minus 20 is like 70 dB of signal to noise ratio. So at 32 times oversampling, we were getting 50 dB signal to noise, and now we're getting like 70 dB when we've gone up to 256. So this is kind of sad, because from 32 to 256 is an enormous increase in processor power, and we only got an extra 20 dB of signal to noise ratio. Just for fun, let's go way up. 4096 is 4,000 times oversampling, just to see if this is actually going to solve the problem. Is this for real? Something must have gone wrong here. Okay, sorry. Something did go wrong. While I was copying that file and running the script, this software was still running, because at 4,000 times oversampling, it doesn't instantly output the result. It takes 10 or 15 seconds just to compute a 5-second sine sweep. So now we will see the result at 4,000 times oversampling. Finally, we have something that looks pretty clean. There's still a little bit of aliasing noise over here, but this is definitely not audible, especially not when you're distorting at this level. Let's have a look at the spectrum. Right, now we're down to negative 110 dB at the noise. That's the noise floor. When the signal is at negative 20, that's like 90 dB of signal to noise ratio. And that's definitely acceptable. And it looks like if we would, I'm estimating that if we would go up to about a factor of about 20,000 times oversampling, we would get to the point where we wouldn't see this noise when we open the file in Izotope anymore. So that lets us know what we're working with in terms of the aliasing situation. I think one of the things we can conclude from this is that there's no hope of cleaning up the aliasing just by oversampling. That clearly it helps. If we go back down to, I mean, reasonably we could oversample with a factor of 32. We cannot oversample with a factor of 4,000, because that's way slower than real-time audio processing. So let's go back to the 32 times oversampling. So we could do this. We could probably make a plugin that runs with 32 times oversampling, depending on how complex the audio processing code is. That could be doable, but that doesn't eliminate our aliasing. So what this tells us is that if we want to make a saturator that can take 100 decibels of input gain and not alias, we're not going to get there just by oversampling. I'm not saying we won't oversample, but oversampling alone is not going to solve the problem. What we need in order to get to that 100 dB gain boost without aliasing is we would need to come up with a different way of doing the wave shaping, or do something like wave shaping, but do it in a very different way that doesn't produce so much of the aliasing noise. So that's what I've been working on for the past 5 or 6 weeks, is we've been just experimenting different ways of doing overdrive, saturation, distortion, and doing it with less aliasing noise. Now, what I found is that we've been able to identify certain techniques that have much less aliasing noise than basic wave shaping does. But after, like I say, probably 6 weeks of looking, we realized that probably we're not going to find a zero aliasing saturation technique. But what we did find is some techniques that have no aliasing below a certain frequency range. And that means that we can combine those techniques together with oversampling, and then we can get a real solution to how to do saturation without aliasing. So I'm going to open another Xcode project, not this. Is it here? Here it is. I'm going to open this other Xcode project, and this is where we've been working on a saturator that can take 100 dB of gain boost without aliasing. Are we running this now? There it is, it's running. It's a little slow to start up the first time. So let's load that output file. There it is. And when I get back here, test. So this is it. We're putting 10 dB of gain boost into our saturator plugin, and we're seeing no aliasing coming out. I'm going to take it up. Let's not waste time. Let's go right up to 100, just to see if this really works. So here's 10 dB of boost. Here's 100 dB of boost. And the time is fast because we're not oversampling by a ridiculously high rate. Output looks fine. And let's look at it in the frequency domain. So there we have it, basically. That's 100 dB of gain coming into a saturator, and between these lines, absolutely clean. If we look at the spectrum, we see, I'm not sure if this is noise or if this is a problem with the way the spectrum is computed, but it's down at like negative 130, 140 dB, which is right down at the bottom of the noise floor. So you can see as we click around, this noise on the side here, that is definitely coming from the spectrum analyzer and not from the tone itself. As we click around here, we can see this is doing all the distortion harmonics that an analog hardware is supposed to do, and none of the aliasing noise that we didn't want. It's interesting to look at the wave. First thing we notice is there's a little bit of distortion in the amplitude, and that actually will do some correction for that later. But the next interesting thing is to look at the shape of these waves. So if you've ever looked at a tube amplifier on an oscilloscope, looked at a tube amplifier output, you may recognize this shape, that this is something typical of the way that tubes distort, that they tend to have this spike up front on the wave, and then they kind of taper down on the back end. And also if we look at how that changes as we go up to higher frequencies, at some point you'll see that shape isn't happening so much anymore. There's not so much of a spike on the front, Let's go up a lot higher. And then at some point it gets quite rounded. So this is really important, it turns out, in terms of determining how to apply distortion to an audio signal without aliasing. It turns out that you can't apply the distortion so heavily on the high frequencies as you do on the low frequencies. You can see that in the frequency domain too. By the time we hit this frequency, which is half the Nyquist frequency, there's no more distortion applied here. And that's because there's no way to distort these frequencies without aliasing, because when you apply distortion, you're going to add higher harmonics, and the next higher harmonic would be twice this frequency, which is off the scale already. So that is that's probably a good point to end this video. I'll talk a little bit about how this kind of saturation works. So if we go back to the original wave shaping that we had here, coming back here, so we have these, functions that sort of change the shape of the wave, like this is doing. When we do this, the danger is that when we change the shape of the wave, we're creating these harmonics, and the harmonics might be, they might create a wave shape that can't really be represented in the audio system we're working with. Let's go over here. It's really easy to see this when you're looking at the actual samples. So here I'm right up near the highest frequencies that the audio system supports. And if you look at the waves here, they go up and down, and there's just these square points are the samples. And the problem here is that you can't really shape these waves, because in a digital audio system you don't have control over what happens between here and here. The blue lines are out of your control. You only have control over the samples themselves, these gray boxes. So if I wanted this blue line to curve it in a different way, I don't have that option here. And if I try to do it, I'll just end up, I'm going to be moving the gray boxes, and the blue lines still aren't going to curve. And that's because at this high frequency, I just don't have enough sample rate. They're not giving me any points in between these two places. So there's really nothing I can do to change the shape of the wave up at this point. And that's why when we look in the frequency domain up here, in this range here, you can't do wave shaping up here. You have to be totally done wave shaping by the time you hit 1/4 of the sample rate. Let's have a look at the wave at 1/4 of the sample rate. You can kind of see why that number 1/4 of the sample rate is significant. I guess you don't really see it here. Suffice it to say that if you want to do, you want to do some kind of change in the curve, like what we're doing here, you have to have enough samples there so that there is some sort of curve to change. Otherwise the curve is something you imagine to be there, but there's no curve there for you to edit. You've just got these samples. That's all there is. So what we're doing with this saturator is we applied some very ordinary wave shaping function. In fact, I used the hyperbolic tangent. That's right here, exactly this same function. You can see it in my code. I won't show it to you, but it's there. And then we created a control signal that would, we asked the question, okay, so let's say this is the input and this is the output. And we asked, what would be the volume control change that it would take us to get from here to here? And so we can do that. Actually, if you just take this divided by this, you get that control signal. And then we said, okay, so that if we would multiply that control signal by our original signal, which is equivalent to just adjusting the volume, almost like having an automation in a DAW that adjusts the volume, but it adjusts it so fast that when this thing is bigger than this thing, it's pushing this one up, and at the top where it's flat, it's kind of pushing it down, and it's updating sample by sample, updating the volume. So we have this control signal that's creating this wave shaping, and we found that you can just low pass filter this control signal, and what that does is it prevents the control signal from moving too quickly, from moving at too high of a frequency. And ultimately what happens then is you get good distortion at the low frequencies, but as you go up in frequency, the saturator is less and less active until by the time you reach this 1/4 of the Nyquist frequency, the saturator is done. It's not saturating anymore. And so it just because you filter the control signal in a correct way, you can then use that control signal to indirectly apply the wave shaping back onto the original signal and do it without without creating all that noise and aliasing. Now I've left a lot of details out. It turns out that if you just do what I said, that would not be, well, that would be enough to stop aliasing, but it would also stop the sound from coming through. So you would only get the low frequency noise coming through and everything else would be quiet. So we have to do some other things, but that's beyond the scope of the video. I just wanted to show you that because I think definitely we're planning on releasing a saturator plugin using this technology, but we'll also be moving on and using it in some other plugins because saturation is a nice effect to fatten up the sound, and it's something that can be used in a lot of different contexts to give you a lot of different sonic characteristics that are familiar for those who use analog hardware, but often difficult to do in a digital context without creating a lot of extra added noise in your signal. So I'm going to stop the video here. If you're interested in this kind of signal processing technology video, consider clicking subscribe on the YouTube channel, and that way next time we do a video like this you will be well, not necessarily notified. I guess that depends on your notification settings, but at least it'll be prioritized in your YouTube feed. See you next time. I think we'll probably be doing this saturator plugin soon, so we'll do a little bit of head-to-head comparison with some other saturators when we release that plugin.